everyone, how are we doing? Who's all here today? It is time to do some learning. It's office hours. Who do we got in the chat? Say hey if you're here. Anyone here? I saw there were like 2 or 3 people watching. Anyone? Afternoon office hours are canceled. Feeling a little, had to get a lot of sleep last night. Got like 9 hours trying to catch up. Coffee's just not doing it. So I didn't schedule afternoon office hours today. I'm like, okay, I'm gonna take a break. Taylor, good to see you. Good morning, Taylor. Brian's gonna take a small break this week. Fall break's coming up next week. Small break this week, but we have a lot of work. Hey, Ford, good to see you here. Good to see you, Ford. We've got a lot of work. What should we do? We've got 201, we got 320, we got 474, so we got to do a lot of work this morning. Class coming up. If you have questions, drop them in the chat. Just saying hi. Oh, thank you, Ford. That's really awesome. Ford, 1,000 points. I appreciate that, Ford. Just all the positivity. That's what we like right here. Just cheering each other on, giving some positivity. It's chapter 5, quiz 2. You bet. Which one should we do from that, Taylor? You call it. Which question are you working on? Remember, name the question, we do the question. That's the name of the game right here. Name the question, do the question. Getting loaded up right now as we speak. This one is coming up due. Is it due tonight? Ooh. Let me look. The thing with teaching is you juggle so many due dates in your head. You're like, wait, so when is this due? When is this due? And 201 has a lot of due dates. Let's see right here. It's due tomorrow night, I believe. Tomorrow night. Ooh. Tomorrow we're gonna see a lot of questions on it, but we should do questions today. I was like, it's coming up. It is here soon. Let's see. Which one should we do, Taylor? You can name any problem you want. We'll do that problem. I could pick one. You could say you pick one. Start from the beginning. But you name it, we do it. And then you want to think about how this applies. Computers. Oh, no worries. I thought it was like the question, like the computer's being slow. A computer runs at a speed of this, with a mean of this, and a standard deviation of this. What is the probability that your computer will take over this amount of time? I was like, is there a computer being slow one? Is that a new one this semester? Chapter 5 is probably one of my favorite chapters. Everyone hates it, but it's a really good chapter. NFL data, actually, no joke, right there, right now. Taylor, I was just like, I see this question right here happening. I was literally on this question as you said it. So Stat 201, Chapter 5, Part 2, NFL data. Okay, let me re-timestamp this again. Forgot to make trades in fantasy. Okay, here we are with the NFL data. Let's take a look at it. So for this question, we're dealing with the running yards, right, or the passing yards. So gained from receivers. So there's the receiving yards of NFL wide receivers. The mean is this, and the standard deviation is this. Now, what's the first thing you notice if you go one standard deviation below the mean? Like if you think about drawing this out, and you go one standard deviation below the mean, and just round these, it's much easier if you just round the data to 250 and 300. So let's think about how we would draw this. If we go here and say the mean is 250, I'm just doing rounded numbers. It makes the problem a lot easier to deal with if we say normally distribute with a mean of 250, which is about the mean that they said, and a standard deviation of 300. Remember, this is NFL wide receiver yards. So what's the first thing you notice about when you draw this out? So a mean of 250, which is going to be the center of the curve, and then the standard deviation is 300, which is going to be the units we go up each time. So what do you immediately notice when you do 250 at the center, and then you go down 300 each time? What is going to happen very quickly to this distribution? What is going to happen very, very quickly, and we see it right here, and I'm using rounded numbers to make the problem easier. Remember, this is running yards for NFL wide receivers. What do you notice very quickly down here with these numbers? That's like, I don't know if running yards really is well, I don't know. That's running yards? You're telling me, what do you notice about it? Remember saying, what do we expect the running yards to be? Like if you collect data on NFL wide receivers, not just a big jump. Good answers right there, Taylor. Good answers. Like who would you, I don't know if you, I don't watch a lot of football. If you ask me to name one wide receiver right now, I'm trying to think who's a wide receiver. The guy, I'm trying to think who's a wide receiver. Gronk no longer plays, and he was a tight end. Gronkowski. I'm just trying to think. I should know my team. There's a guy with an interest. They all have interesting names. There's a guy in the NFL. What a wide receiver. And so they're going to catch the ball and they're going to run with it. Brian can't name one wide receiver. Sad day. Tom Brady. He's wide receiver. I'm just kidding. Some football person's mad at me right now. So the wide receivers getting negative yards really doesn't happen. The only way you're going to get a negative yardage is in a play where they do a backwards lateral to you, I guess, and then you get tackled. So I think that would count as negative yardage. And so it rarely happens. And to have a whole season where you accumulate negative yardage doesn't happen. So the normal model is probably not going to be appropriate for this data because it would say that we would expect, and let's take a look at it, and this is where this problem is going to go, if 68% of wide receivers would be within plus or minus 1 standard deviation. Does that make sense right there to say that, Taylor? That 68% according to the normal model should be plus or minus 1 standard deviation. So then we would expect the 16% of wide receivers to get negative 50 yards or less. So there's going to be a lot of wide receivers in the NFL doing horrible. And frankly, you could just, I don't know, I could be in the NFL with these sorts of like abilities to be like, oh, just pass me the ball and I'll just drop to the ground. I'll be like, no, don't worry. I'm just going to catch it on the line of scrimmage. I'll just get 0 yardage because I'll be better than the worst. But no, that's not how it goes. Really, when it comes to yards in the NFL, the distribution is probably right skewed. So you're going to see something more like this, with 0 being around here and like next to nobody that might play in one game would get negative yardage. So you'd really see rare to never that someone has negative yardage to end a season. And then you're going to have like your top tier wide receivers, which are a small group. Your all-stars, like this is your all-stars. These are your first, like your top wide receivers, your seconds on your teams. And this is like your general, your third. And then this is just like everyone else. So you kind of get these groupings right here of wide receivers based on the amount of yards they get in a season. And it's not going to be normally distributed. Probably it's going to be right skewed. According to the normal model, what percent of wide receivers do we expect to gain more yards than 1 standard deviation above the mean number of yards? So if we go 1 standard deviation above the mean, I have too many documents. What percent of wide receivers would we expect to get more than 1 standard deviation above the mean? According to the normal model, this number right here, I'll circle it in blue. I already used blue. What percent, that right there, Taylor, 1 standard deviation above the mean, we'd expect what percent of the wide receivers to get 1 standard deviation above the mean? And I've got hints on the screen. I've got it drawn out. Remember, always draw this out. So I've drawn it out right here, and we're looking for this number right here, 16% exactly. So it's doing the empirical right there. We should be right on 16%. If you're a decimal off, let me know. Sometimes people use the applet to get these answers. It should be nice-ish on it. For these data, what does this mean? About blank receivers should gain more than this yards. So it's telling us right here there's 508 wide receivers. So we want 16% of that. So we would say here 0.16 times 508. We're going to round that to the nearest whole number. We're going to round it down. Doesn't say round up. Round to the nearest whole number is needed. So 81. And once again, what I did is we're expecting about 16%. So that's 16% of 508. I think there should be about 16% of these wide receivers getting that much yardage. And we would times it by 508 to say 16% of that and round it accordingly. Now, to do the 1 standard deviation, we're actually going to use the real numbers. Remember, I'm estimating it to be about 550. The reason I'm estimating that is it's 1 standard deviation above the mean. So we needed to do the formula, the mean plus 1 standard deviation. But let's plug in the real numbers right here. So we need the mean, which is going to be 25 right there. 253.764 plus 1 standard deviation, which is 312.359. And there it is right there. Round to the nearest whole number, that should be 566. Explain the problem in using the normal model here. The normal model is for only normal data. These data are, let's take a look at it. Whoa, wow. Look at how I drew this out. They do have some negative right there. So if you look at my drawing on what I thought it should look like if we actually use the real data, it's going to look something like this right here, which is what we see and what they're showing you the data apparently looks like. So using the normal model for this is a horrible idea because the data looks more like this, where you have the kind of your general like average team player, your good players, your first tier, your all-stars, and your phenoms, your amazing players. The normal model just doesn't work for this. So the data is strongly right skewed. The normal model is not appropriate. Yes, we like that right there. They changed this question a little bit from last semester. Really good question. I was a little afraid on the empirical rule number. More exactly, it's 15.9. I think if you, so it is saying we're correct. Where is the boundary on this? Oh, it is right there. The boundary is right there. If you want to go very exact on it, it'd be Q norm -1. Oops, Q norm. I didn't spell Q norm right. Oh, it's P norm. I always get P norm and Q norm confused. Oh my, not bracket norm. So it's 15.9. So if you do that right there, does that make sense, Taylor? Don't worry about P norm. That's what I'm doing is I'm actually running. If you ever do the David M. Lane, the David M. Lane will get you the exact percentages. So it will take the exact percentages, and luckily it also takes the empirical rule estimate. So one standard deviation above the mean is going to be this right here, 15.9 right there when you round it. And then also using code, which everyone knows Brian loves using code, I could take and find 1 minus and get the other side of the curve. That's just the graphical error, and do that right there. Yeah. So this is the exact answer using code because there always are more decimals. Wes, what's up? It's stats time here. Drop some more questions. We're showing how to get, the answer with the empirical rule. So we showed basically 3 ways to solve this, from kind of the most basic way to get 16%. 16% right there is obtained from the empirical rule. That's my preferred way to solve this, which you can always use on the test. So we figured out that this was 16% by doing 68% inside, thus 16% is outside on either side, half of 32. Then we also solved it with the David M. Lane by showing it visually right here to get the exact answer of 15.87, which rounds to 15.9. Then we did the advanced way of doing it via code right here, because the great thing about code is if someone said, well, I want to know a crazy amount of digits, you say, well, there you go. That is the insane answer right there. That is all the decimals. So the empirical rule, people say, well, why is it different? The empirical rule is just a rounding. It's not perfectly 68% inside of it. If you really want to get down to it, it would be the exact percent inside of it would be that 68.2689, but we just round it to 68. That's when we say 68, that's what we're saying. 95 is 95.4495, I think. 95.4499, there we go. And then 3 is 99.73. There's the 3 and then the zeros. Actually, so says mine says 2 standard deviations above the mean. So if it's 2 standard deviations, what is the area above 2 standard deviations? So I kind of just showed it. So here's the important numbers that we use: 68, 95, 99.7, 68, and they're there. It's just more decimals. 68, 95, 99.7. So what is the area outside of 2 standard deviations? What is the area outside of 2 standard deviations? Yeah, so the area, for those wondering if you're also solving the same problem, Taylor's solving. Great job, Taylor, right there. We need to go back to our graphic. The answer was on the screen a moment ago, but I'm going to show it here with the graphic. It helps to do things visually, and then we can solve it. And then we need to add 2 standard deviations when we go up. So we want to go here and go 2 standard deviations and do according to the normal model. And this would be 99.7 or 95, excuse me. See, I'll make mistakes there too. And then outside is total 5%, but that's 2.5 on either side. So I'm guessing this is what you got, Taylor. And the problem is going to work the same way theoretically. We should get an answer. Remember, I'm using estimates here, about 850 by going 2 standard deviations up. We're just taking the mean right here, mu, and going up 2 standard deviations. And you can see it right here visually. We're adding to it standard deviation to get 850, going up 300 each time. So there should be about 2.5, but I think you won't find that. Taylor, keep asking those questions. We have no other questions right now, so I'm just expanding on how to use the normal model and how to draw it out and how to understand these questions if you get something like this on the test. where it might ask you to find these answers, because you won't be using this on the test, but you use this sort of knowledge of the 68, 95, 99.7. So knowing how to solve this stuff is what's important. It's not about just one problem. It's about the theory behind it. Like, well, wait a minute. If it says 2 standard deviations, how would we do it? Well, we can find the area outside of 2 standard deviations. So above 2 standard deviations would be 2.5%. Okay, well, what other questions do we have? Let me see here. Let me check my knowledge. Because 4 standard deviations should be 99.99. Let me times this by 100. 4 standard deviations, Brian's checking his knowledge right here, should be 99.99. That's where the 9's end. 99.99. And then 5 standard deviations is 99.9999. It adds 2 more 9s. There it is. There's the 2 9s. Now, 6, this is where it gets cool, is 99.999999. And there's the 2 extra 9s right there. Almost rounds to the next one. Now, 7 standard deviations is only 1 extra 9. So it's 99.9999999. It only adds 1 extra 9. No, it does. It adds an extra 9 on top of it. Oh, Brian got it wrong. Okay, I got to put that back in my head. It adds an extra 9 on top of it. So the 7 standard deviation adds an extra 9 to the 99s. It's just me being ridiculous. Speed of cars. Let's do that here. Brian's going to stop being ridiculous with trying to memorize numbers. I don't know. I love numbers. Numbers are just cool. Like the patterns they have, what you can learn from them. Let's do the speed of car ones right here. And Brian's going to re-put the empirical rule to 7 standard deviations in his head. He got noted out to 7 standard deviations, which is ridiculous. Speed of cars were measured. Looks like it's normal probability plot 1. Got noted to 7 standard deviations. What? Chapter 5, part 2. Let's do it. Here we go, Taylor. Oh, yeah, we got the speed of cars right here in a normal probability plot. So we are using this all the time in 320. When you have a normal probability plot, what does it show us? It shows us the probability, a what is what. Like a normal probability plot, which is this, shows us the what, that a what is what. And then let's look at how to analyze it. So Taylor, what does a normal probability plot show us? Hey, what's up, Evan? Great to see you here. What does a normal probability plot show you? It shows you the this, that a this is this. So what does a normal probability plot show you? It shows you a this, that the this is this. What does it show you? I might try to make this even cooler right here. Can I do this? Let me try something. We're going to try something. Shows us the probability. It shows us the probability that a plot is normal. The probability that a distribution is normal. And so I'm going to try to make a really nice graphical display right here. I don't know if this will work, so I'm going to... Cool. There we go. Let me try this. Cool. Can it do this? It can't. Okay. Well, let me just do it the normal way then. Okay. So with this right here, I turned and right. Oh, no worries, no worries. It shows the probability that plot is normal. So let's look at this right here. Is this histogram, does it look normal to you? Just yes or no. Does that histogram look normal? Just a yes or no. What does normal mean? Does this histogram look normal to you? Yes or no? And my gosh, that's a, yeah, I'd say yes. It is unimodal and it is symmetric. So when you think about normally distributed data has the 2 characteristics of unimodal, and it also has the rule of symmetry right here. So the more unimodal, the more symmetric it is, the more normal it is. So I'm using the same sort of idea right here to create what we call a normal probability plot, and this is the plot that tells us the probability it's normal. So let's add a quick title to this, and we'll say title, normal distributions follow the red line. So normal distributions follow the red line. Does this plot follow a line? Does it follow that red line? I love it. And it's kind of, we wouldn't really, and that's the thing, so don't worry. It's kind of like, it doesn't have a linear relationship, or I guess someone could say that the expected values follow the observed values linearly. I guess they could. We generally just look at this and say that This is what we expect when it's normal. So this red line down the center is what I expect when it's normal. So it follows the line. So, and this is a special type of plot. So when we do regression coming up here soon, we won't say that it's like normal because it follows the line. This is a special check because it's a normal probability plot to tell us if it's normal. So we have a line that says like, this is your guideline. If it's normal, it should generally follow this. Does that make sense? Like if it follows that red line, it's pretty normal. And these are your kind of, these dash lines are kind of like your, yeah, like, meh, it's kind of okay. So this pretty much follows the red line. It doesn't really have any deviations from it. But let's change this up right here and use different data. If we use this sort of data, does that data look normal? This is an exponential distribution. Does this data look normal? It is unimodal. It does have one mode. It is unimodal. Does it look normal? It's missing the second characteristic. No, great job, Evan, right there. It's missing the second characteristic. It's skewed. So we could say non-normal data, or we could say not normal. Not normal data does not follow. Not normal data does not follow the red line. And take a look right here. Not normal data does not follow the red line. Not normal data does not follow the red line. Look how far away it is. The data does not follow a linear pattern for the normal probability plot, so that tells us whether or not it's normal. So once again, if the data looks normal, unimodal symmetric, it's probably going to follow the normal probability plot pretty well. Don't worry if it's a little weird. It's pretty okay. Not normal data is going to not be unimodal symmetric, and then we got some outliers over here. And this is a right-skewed data set. If you're trying to figure out which way it's skewed, if it's pushed to the right, that's the way I like to remember it. Think of it as like a gust of wind. Like you got someone over here. I'm going to try to draw a person. Here's Brian. And we're like, woo, gust of wind, woo. There we go. So that's my top tier drawing skills. Gust of wind, it is right skewed. And when you have right skewed data, there's my OBS right there. When you have right skewed data has a tail to the right, blowing out a piece of paper right there, blowing it to the right there. So that's also right skewed. And we always like to remember our monster man for right skewed data right here. You draw your monster man. I can draw monster man much better. There we go. There's the monster man, and he's got a right skewed tail. So that is right skewed data right there. So let's take a look at our question. Okay, does this follow? We've got a little outlier over there, which you see right there. Does this mostly follow a line? Like if you were to put a line through this data, let's see right here. Unimodal symmetric, decent. Line through data. What do you think? Does that mostly follow a line? Mostly. Yep, exactly. And that's how you look at a plot that tells us the probability it's normal. It mostly follows a line. It's mostly normal. So let's take a look at the answers. Is a normal model appropriate? Yes, the histogram is unimodal and symmetric, and the normal probability plot is straight, which means it follows the line. There you go. Good stuff. Good question. Good review of normal probability plots. We didn't have questions usually on this, but we've added them this semester. It's a really good review in understanding when to use a normal probability plot because we need to know our data is normal. So if we go back to this first question here, and if we did a normal probability plot, what would the data look like if we did a normal probability plot for this? If we did a normal probability plot, how would the normal probability plot look for this data? Do you think this plot follows the normal? So the normal probability plot, if we ran it on that data, would probably look it wouldn't be normal. It would show this pattern right here. So this is what I wanted to show, is the data right there is heavily skewed. It's right skewed. And then you would see something like this here that doesn't follow the normal. And you can kind of think of I can't draw on the other one, but if we could draw a red distribution over this, it doesn't follow the normal. I mean, maybe there's a buildup of data here, but down on the low side, it doesn't follow it. And that's what you're seeing down here. It doesn't follow it down here. And then there's a buildup of high values over here on this side, especially like this outlier. This is not the exact same plot, but that does kind of correspond to this point over here, which is an extreme outlier. And then you've got a little bit of buildup. No, which way is this skewed? Which way is this skewed, Evan? Good review right here, 100 points. Which way is this data skewed? Which way is this data skewed? Which way is this? It's right skewed. Exactly. It's right skewed. So you got your little person right here going like, woo, blowing it to the right there. So it's skewed to the right. That's right skewed. Great job, Roshni, right there. And drop more questions in the chat. We're just doing some practice right here, talking about the way these look and how to analyze these and understand what a normal probability plot is and how it tells us the probability a plot is normal to check for normality to see if we can use the empirical rule. More questions, drop them in the chat. Really good review, everyone. Good review of normal probability plots. What other questions do we have? Let us know. It's little things like that, like trying to find ways to memorize them, because you can go to the deeper understandings, like how to like plot it and draw it. But then a lot of times, we just have to have the knowledge of how it works. So you gotta put it in your head, and then you have to like use that to gain a deeper understanding. It first has to live up here. Use the normal probability, find the weights of steers. Okay, let's find it. We might be able to do all these. Cool, we got some David M. Lane right here. Canvas content numero 4. We could do that. Es muy bien. Me gusta canvas content. Tengo mucho tiempo ahora por canvas content. Weights of steers. Okay, we got some weights of steers. Let's go check it out. We'll do some canvas content too coming up. Let's check it out. Okay, we've got the weights of steers. Where do you think we're going to go for this? Where do you think we're going to go for this? Anyone got any clue? Where are we going to go? Where are we going to go? I need some... We're going to do some drawings. I like that right there. We're going to go to David M. Lane, too. We're going to draw it out. We're going to go to David M. Lane. We're going to take some guesses right here. So the 56th percentile. Let's look at 99th first. And I can get a 66 on this question without David M. Lane. Just to show you really quickly, and then we're going to draw it out. So try doing your drawing here while we're talking about this. But I'm pretty sure I can get a 56 on this question, or a 66 at least on this question, without going to David M. Lane yet. So people will say, well, how would I do this on the test? We're going to show how to do it on the test right here. Where my boy Blake at? Where is Blake? So here we go. The reason I get a 56 or 66 is I know a lot of the things via the numbers on the curve, which are constant, like z-scores. This is the only one I'm a little worried about that I don't think I'm going to get. Now, the 56th percentile, so Brian's solving this right now using his knowledge. Then we're going to use David M. Lane to solve it. I'm just showing you can get some of these right. Okay, so the 56th percentile is a little bit above the mean, but it's not quite one standard deviation. It's actually kind of close to. So this is the only one I'm really afraid I'm going to get wrong. This one right here, that one's a really tough one to guess. The 99th percentile, the z-score for the 99th percentile is 2.3263. So I times that by 84, and I know that because I've done this a lot. And so that's going to round to the nearest whole number as needed, 1339. The IQR goes out, oh my gosh, why am I not remembering now? 0.6726. I'm a little afraid I've got that one wrong. So we need to times that by 2, 0.6726. Is that right? Times 2 times 84. Round to the nearest whole number. Did I get 2 of these right? And the answer is 66, like I said I would get. How'd I know 2.62? Oh, 2.3263. The reason I know that, and great question right there, Evan, you're not expected to know those things. I have done these problems tons and tons of times, so I know the z-score for a 99% confidence interval, and it's 98, excuse me, because, 98% confidence interval is 2.3263. 99 is 2.5758. So the reason I use the 98% confidence interval is because if this is a 98% confidence interval, follow me with this logic, because this is how it could look on the test. If 98% is inside of here, what is on either side, like just by itself? If 98, this is how Brian was solving it, like you could get this picture on a test. 1%, right? So this mark right here is the top 1%, and we could use the thing right here to solve for us and say the top 1% is there. So I was able to know that knowing 98% inside, 2% outside, 1% on either side. This is where the top 1% is. The top 1% is also the what percentile. This is test teaching right here. The top 1% is where the what percentile is. Remember, percentile is area below. So the top 1% is where what the what percentile is. The 99th, exactly. So you could also show this by doing this, and you have the 99th percentile. This is what you need to know for the test or understanding of the curve, that percentile means area below. You could get any of these pictures on the test to ask you to solve the problem. Like if you have this right here, what you want to do immediately is start drawing on it. You want to say, okay, that's 98%. Since this is 98%, here's what I would draw if I had this on the test. On the test, I would mark 98% in the center. I'd mark 1% here. I'd mark 1% here. This is the first percentile, and this is the 99th percentile. The z-scores associated with this are going to be this and this. So this is 2.3263, or I'll write the number it says, and then 2.326. Does that make sense on what I've done right here? Like if this was a test question, you would get this information right here, and you would have to solve it using this information. Now you might say, well, how could we solve this? What does the z-score tell us? The z-score is telling us what? Great job, Evan, right there. The z-score is telling us how many whats. The z-score is telling us how many whats. What does the z-score tell us? Because we want this answer right here. Standard deviations above the mean we are, right? So if we take the mean and we add to it the z-score times the standard deviation, we will get the observation. Because we're just going here to the mean and adding to it that amount of standard deviations. So we need to times the standard deviation by the z-score and add it to the mean. This is where I took the numbers in the problem and I was solving it by going right here and taking, we're doing the second one currently, 1,144. And the z-score is 2.326 times 84. That is where we obtain the answer, and you can even use the applet to solve 1144, 84, and now it plugs in the numbers. Now we no longer see the z-scores, we actually see the answer to the question, which is 1,339. Does that make sense right there? So now I'm seeing it with the context on the curve, so you can see the difference between the curve with the z-scores, we would get the number 1,339, and so we get the answer right here by solving with the z-score, versus if you're doing it by yourself right now, you could just plug in the numbers and get the answer. Who's following right here? So this is the answer to the second one and how to visually show it. I would alternatively, if I'm solving this, just put in the 99th percentile and solve it this way. Which means if we want the 58th percentile, what should I do to get the 56th percentile and get the right answer right here? Which I don't have that one memorized. That's not a common percentile we talk about. What should I do to get the 56th percentile right here? What should I do for this question to get the 56th percentile? I'm on the David M. Lane applet. I'm graphing the area below. So what do you think I should do to get the answer for this? I've got my mean and standard deviation. I've got the second button clicked. I've entered in my mean. I've entered in my standard deviation. So what should I do to get the 56th percentile? Now, if you look, 56th percentile is somewhere a little bit above the mean. So I can get it pretty quickly. What should I do? Just change the area, right? Great job, Evan, right there. Just go right here and go 56. And it's 1157. How close was I? Oh, I was 5 off. A decent guess, right? So now we check our answers and we get the 100. But the last one right here is a bit interesting. The reason, exactly. Is it making sense, Taylor? So you can just find the area below that, and that's the percentile, and then you have the answer right there. And remember, make sure you understand visually what you're seeing. Like the 56th percentile means 56% of steer weights would be below this weight. So that's what the percentile means. It means below this point is 56% of the data. The 50th percentile is what? Like, just use your knowledge right now to tell me the 50th percentile. You should be able to solve it like this if you understand what's going on right here. We're doing a few checks, and we're going to solve the last one here real quick. This doesn't have correlation yet. Making sense. Nice job, Taylor, right there. And great job, Evan, right there. Let me know, Evan, which one you might be working canvas content. Let me know which one. That is correct right there, Evan. Now, here's a harder one to get that you could be asked on the test. Where is the 84th percentile? Where is the 84th percentile? We'll throw 1,000 points if you can tell me, and then we're going to solve the last one. But we're trying to get people test ready right here and tell you what could be on the test. A very fair question is, where's the 84th percentile? You say, how would I even get that? Well, think about what you know with the empirical rule. And the answer's on the screen. It'll be very close to this. We would accept this answer. Like, we'd probably put a range of like plus or minus 5, because if you basically get it, someone could put it into the TI and get the exact answer. But who would say like round to the nearest whole number, where's the 84th percentile? And so we want to be on the right side of the curve. And if no one knows, that's all right, but take a guess. Great. Oh, close. Evan, do you want to update your guess real quick? Evan, do you want to update your guess? Sorry, let me zoom in a little bit here. I think you see it, Evan. Do you want to update your guess? Well, no. Your answer looks... Yeah. Because... Great job, Evan, right there. 1,000 points for everyone. Because think about this. If we were to talk about... Oh, let me go this. The 0th percentile. There we go. If we were to talk about between here and here is 68% of the data. So outside is 32% total. So how much area is below that line? How much area is below here? Let me zoom in on a little bit here. How much area is below there? 16% is above. So 16% is the above. Good work, Evan, right there. 16% is the above. That's how much is above. That's 16% above. And then there's 84% below. So that makes this spot right here, this makes this the 84th percentile. Does that make sense why that's the 84th percentile on the curve? There's 84% of data below there. There's 16% above, and that's why we call it a percentile right there. That is the 84th. Yeah, exactly. So that would be a decent test question because it uses the empirical rule, and we could check it right here by going to 84th. And your guess, if you round that, that is literally 1228. So if you look at it, you just solved that with the empirical rule right there. If I ask you the 97.5th percentile, that would be the top 2.5%. So we should get about 1312. It should be close-ish to that, right? 97.5. There we go, right there. And that one's a little further off, but that's the answer we would want because it's 97 point. Oh my gosh, it's 95.449. So we could, yeah. We talked about this earlier. If you want to know earlier, we talked about the exact percentages on the curve and went super far out. So the last one right here, people are probably wondering, well, how would you get the IQR? Well, the IQR, this is review, is the middle what percent of the data. The IQR is the middle what percent of the data. Here's a hint on the screen. The IQR is the middle what percent, the middle 50. Great job right there. Wes, good throw you 100 points, 1,000 points right there. Throwing some big points. Good to see you. Blake showed up. We love it. And then we got everyone with some questions. So we're going to do some Canvas content, drop more questions. Got a lot of time. So the middle 50%. So how would I find the IQR right here? How would I find the IQR? How would I find the IQR? How would I find the IQR? What could I do with those numbers to find the IQR? Because this is Q3. This is Q1. We could find them respectively by doing... subtract them, right? Just the distance. This is what's the distance of those numbers on the curve? You could find Q1 by saying this, or that's Q3, that's Q1, the bottom 25%, the top 25%. Q3 is the top 25%. You could just subtract those numbers, or you could find both numbers by doing the middle 50%. Take right here, subtract your numbers, and you now have the IQR. Now, the reason, if you're wondering how was Brian able to solve this, and there's the answer right there. I know the z-score for the middle 50%. It's 0.673 or 0.6726, I believe. And so the z-scores never change. So I use the z-scores. So 0.673. Let me look at that over here. Q-norm is Q-norm, right? No, P-norm. No, we want Q-norm. 0.6744. Okay, I try to remember that. 0.6745. There you go. So that's the z-score that never changes, and that's what I was punching into the calculator to solve. I times it by 2. Don't worry about solving these by hand. You have to memorize the z-scores, but since I do these problems a lot, I just try to memorize the numbers. But there we go. So that's how I was able to solve it, but you would need to use pictures. But I was talking about running backs and football at the beginning. Yeah! Oh, did we get that one on here? Yeah, we'll probably do Canvas content next. What other questions do we have? Did I miss a question? People asked about running backs in football. We did that one earlier. I think you rewinded. Oh, What other questions are there right now? Should we do Canvas content? Should we do some Canvas content, everybody? Is it time for Canvas content? Yes, let's do some Canvas content number 6. Do that one. Do some Canvas content. You bet. Afternoon office hours are canceled. So I've got some meetings. They said, Brian, we need you. Let's see around here. Someone said the 28th, and I was like, wait, it's a thing for next month on the 28th. Canvas content. No scrubbing. There we go. Let's see. Okay. I've got like 3. I love Discord so much. I've got like 3 messenger apps. So like, I should get Slack also. Then I'll have all the messenger apps. All the messenger apps are mine. All your base are belong to us. Ready for chanting in class today. QQ, straighten up. No outliers. So office hours Friday then? We could probably do that. We could maybe swing that. I think I am slightly free on Friday. Odds are 40-70. Do some betting inside of here. Let's do some Canvas content. We need some Friday office hours. We probably do that. I'll try to do that right here. I think as long as we can. Also, I need to review that. I do Canvas content. Canvas content. 52. Stat 201. Canvas content number 4. Chapter 6. And here we go. Let's do it. I feel like this time I'm going to for sure get that. Nice job. So here we go. Kill me in the chat, you guys. To create a scatter plot, both variables must be what? We should know this instantaneously. Take a look at the graphic right here. To make a scatter plot, both variables must be what? Have this picture if you need it, and Evan's got it right there. Both variables must be quantitative. That's the first condition for doing correlation is you need 2 quantitative variables. QQ, straight enough. Great job, Roshni, right there. QQ, straight enough. No outliers. Plot doesn't thicken. Plot doesn't think it's more of a regression thing, but we kind of use it some. The correlation coefficient of it's not affected by outliers. Really? Let's take a look at that. I don't believe that nonsense. Let me go to view and let me go to actual signs right here. And we're going to go to core demo. So this is a correlation demo right here, which shows you what correlation would be. And let's take a look at a plot right here. If things perfectly follow a line, the correlation is what? If things, nice job right there, Blake, remembering it. If things perfectly follow a line, the correlation is what? If things perfectly follow a line, the correlation would be what? QQ, straight enough. No outliers. This is not the normality thing. If things perfectly follow a line, then they are what? If things perfectly, we're going to do it this class, Evan. If things perfectly, good questions, Evan, right there. 100 points. If things perfectly follow a line, then they have a what? A correlation of 1. Does that make sense? Or -1 if it goes downwards. Blake knows everything. So watch this. You ready? Boop. What happened to correlation due to this one outlier? Did you see it? Watch again. You ready? I'm going to undo it. So there's the correlation of 1. You see correlation of 1? Boop. Did that outlier impact the correlation right there? Watch again. Here's the correlation of 1. It went down. It got weaker, right? It got weak. It's like it's going towards 0. How about this right here? Let's end this and restart it. And now watch this. If we had here a cloud of points, what would a cloud of points have as a correlation? Like what would a big circle of points have as a correlation? I'll try to get it nice and perfect right here. But what would a big circle of points have as a correlation? Like if this is just a cloud of points, a big cloud of points, Mr. T, a big cloud of points would have a correlation close to what? A big cloud of points right here would have a correlation closer to what? Maybe 0. Great job right there. But what if we put a point way over here? Do you think that would kind of create a what relationship? If I could put a point way over there, oh my, what just happened? Or, well, you can't even see it, it's off the screen a little bit. If I put a point right there, or if I put a point down here, do you notice that this one point is rude right there? It's being very rude. It's taking this correlation of 0, and you can kind of see that this looks like a 0. So it's taking the correlation that was 0, basically. Here, we're trying to make it exactly. Oh, man, come on. I'm going to make it exactly 0. There we go. Now it's a correlation of 0. So this correlation of 0 can be changed rather rapidly due to one outlier making it very positive or one outlier making it very negative. So why do we say no outliers? Because anything is possible with outliers. I got to put that on the soundboard for today. We got to go grab that. Anything is possible. We're going to put that on the soundboard. It's got to be down here, I think. Yeah, that's a... Let me clear that.
It matters! It doesn't matter!
Wow.
Okay. We know where anything is possible is going. I got to grab that before class today. Grab some anything is possible. So outliers do anything. The Lego movies is in So where is the it matters?
It matters!
We have it matters on the soundboard now too. Thank you to my student who made that. He's like, I sent you an it matters. We need the Rock to say that though. We need him to actually do it. So the correlation coefficient is not affected by outliers. True or false? What did we just learn? We just did a mini lecture right there because we're here to learn, not just get the questions right. Correlation coefficient is not affected by outliers. False. Now I'm going to drill you for the test. You ready? Outliers can make a weak correlation strong. I'm drilling you for the test. Outliers can make a weak correlation strong. What do you say to that? True or false? Outliers can make a weak correlation. Garrett, good to see you here. Outliers can make a weak correlation strong. True. Outliers can make a strong correlation weak. Outliers can make a strong correlation weak. Outliers can make a strong correlation weak. True. Outliers can make a negative correlation positive. Notice the pattern. Outliers can make a negative correlation positive. True. Outliers can make a positive correlation negative. Outliers can make a positive correlation negative. True. Outliers can make a moderate correlation way stronger. True. Don't worry, I'm not trying to trick you. Because what is possible with outliers? And why do we not like them? Because anything what? What is possible with outliers? I'm drilling you. When you get to a test question on this and you see something like that and it says an outlier can do this, what do you just say? Anything goes. Now, the one thing that is outlier kryptonite, there is outlier kryptonite, and I forgot to mention this one semester, and a student was like, but you said anything is possible. Outliers have one source of kryptonite. The outlier kryptonite is the what? The outlier kryptonite is the what value? The outlier kryptonite is the what value? Hint, that value right there is not changing as I add zeros and make this more of an outlier. The outlier kryptonite is the median. Great job, Roshni, right there. The outlier kryptonite is the median. There's always like the one exception to the rule. So the outlier kryptonite is the median. It just, you can't, median's like, I don't care about outliers, but they can do anything. You're like, I'm the one exception to the rule. So when it comes to correlation, anything goes with outliers. So that's why the conditions in correlation are QQ straight enough, no outliers, because it will greatly impact the correlation coefficient. So do remember outlier kryptonite is medians. I don't know, it might be on the Kahoot Sunday night. Which of the following is not a way to describe bivariate? What are the 3 ways to describe univariate quantitative data? What are the 3 ways to describe univariate quantitative? We took some notes last time. What are the 3 ways to describe univariate? The 3 ways to describe univariate is review shape, strength. The 4 ways for scatter plots are strength, direction, form. Great job doing it the way I usually do it. There's strength, direction, form, unusual features. And then univariate, which is going to be a histogram, is shape, center, spread. So this is univariate if you're looking at one variable. This is bivariate if you're looking at 2. So when we go over here and we say, what is a way to not describe bivariate? We have strength, direction, form, unusual features. These are all correct ways right here. So shape is a wrong way because shape is a way to describe univariate. The shape of it is unimodal. Over here, we look at the strength, which this is pretty strong. The direction, it's positive. The form, it's linear. There's not really unusual features, which are outliers. So that would be the answer right there. Shape center spread is for univariate, and so shape would not be a way to describe bivariate. A p-value for correlation which is statistically insignificant implies that it's due to random chance. So this is a tougher one, and I'm trying to think how much of detail to go into right here to explain this. So when we look at p-values if you're in 320, can you go over homework 4, question 8 for BS? Yeah, split into 2. We'll try to throw it in. Thank you, Morgan, so much. We'll probably do that here next, and that might be what we end with. Good questions, Morgan. Let me put that in the notes. BAS 474, homework 4, question 8. Try to give some tips for that. Thank you, Morgan. So, Morgan, this is a really good question right here on p-values, which we use all throughout statistics. There are two close to 0. Oh, good at Olive, and I'll do that here next. Ooh, look. Oh, wait. I think we'll check. Oh, this kind of answers your question down here too, Evan. Like, tell me if you noticed your answer. So be careful. Maybe you only get a few shots, so we'll check it out. So p-values are the probability what we saw is by random chance. If I tell you that there is a 1% chance of rain today, do you think it'll rain? Just yes or no. I say 1% chance of rain today. Do you think it'll rain today? If I say there is a 1% chance of rain today. No, you'd say I don't think it's going to rain. It's unlikely it's going to rain. So if I say there is a 1% chance what you saw is by random variation. So if I say there's a 1%, would you say do you think what you saw is by random variation? So remember your answer to the first one, not trying to trick you. You don't think it's going to rain up here, right? So if I say there's a 1% chance what you saw is by random variation. What would you say? Do you think what you saw was by random chance variation? There's a 1% chance what you saw is by random variation. What would you say? No, it's the same. No, I don't think it's going to rain today, and I don't think what I saw was by random chance. Does that make sense? We put random chance right here. Random chance is a good phrase. So there's a 1% chance it'll rain today. I don't think it's going to rain today. There's a 1% chance what you saw is by random chance, or 1% probability, we say. 1% probability. Probability. That's about probability if our results more same how my random chance variation given the null is true. So there's a 1% probability it'll rain today. I don't think it's going to rain today. There's a 1% probability what you saw is by random chance. I don't think what I saw is by random chance. Let's add those phrases below. I don't think what I saw is by random chance. I don't think it will rain today. Notice right here. This is what we do. I tell you there's a 1% probability of this. You say, I don't think it'll rain today. I tell you there's a 1% chance or probability what you saw is by random chance. I don't think what I saw is by random chance. So let's look at this. When it asks us, a p-value for correlation which is statistically significant implies that the correlation is due to random chance. Statistically significant means the probability is below 5%. So does this sound likely or unlikely? Does this sound likely or unlikely? If I tell you there's a 5% probability of something happening, would you say, oh, that's likely to happen, or unlikely? Unlikely, exactly. So this sounds unlikely. So when you look at the question right here, the p-value, which is statistically significant, implies it's due to random chance. Well, when we talk about p-values, the p-values stand for the probability of our results, or results more extreme, happening due to random chance variation given the null is true. The null being no correlation here. So when you look at this right here, we would say it was unlikely what we saw was by random chance. So the probability is low that this happened by random chance. The most likely correlations, last bit of review right here, a correlation that is very weak, like an R of 0, would look like this. These dots right here look very what? If there is no correlation, which is the null hypothesis, These results look what by random chance? Hence, we'd put a probability here. Dots. Those dots look very what by random chance? Think likely, unlikely. Do those dots right here look very likely by random chance, given there is no correlation? If there is no correlation in the data, that pattern would be what? Likely or unlikely? If there is no correlation, if it's just no correlation at all, that pattern would be very likely or unlikely. This pattern would be very likely. And the high probability, does that make sense? The probability is 0.98, which is the p-value, telling us it's very likely. What we saw right here is very likely. If there's no correlation, that's a very... No, Rashni, let's throw 8,000 points. The thing is just practicing right here, because p-values are... If you notice the time I'm taking on this, p-values are a bigger concept. We're throwing you 2,000 points, Rashni. We throw big points for all those answers. So the p-value is good to see here, John. The p-value tells us that what we saw here was very likely, given there's no correlation. So if you look over here at this result, the correlation here should be close to what? Who can estimate the correlation here? It should be very close to what? I'm putting some extra dots around it. The correlation here should be very close to what? Close, not one, close, not one. I'm doing a little trick. You're kind of right. Not one, though. Not one, though. Not one. It should be closer to what? Not one. You're very close with one, but you're missing something. You're missing the direction. You're missing the direction. Good work right here. Not one, but negative one. I was like -1. So -1. And does this relationship look by random chance? Like, does it look random? Like this one looks just random scatter of points? Or does it look not random? So here we are with the null that there is no correlation, which this seems super likely. And technically the p-value would be, technically a statistician is going to get mad at me. This was the most likely thing to see. It looks not random, right? So the p-value here is going to be low, telling us that seeing this is very what, given the null is true. If we were to see this, this is a very what likely result. This, what we saw, is very what if there's no correlation. If there's no correlation in the data, seeing such a strong negative correlation wouldn't quite be -1 because it's not perfect. It'd be something like this right here. It's very unlikely. So a small correlation close to 0, like if this was a correlation of like 0.02, the p-value would be something about, because it can be tiny, and the p-value is going to be something like this, saying this is very likely to see given there's no correlation, where this one over here says this is very unlikely to see given there's no correlation. P-values are going to be very important for later chapters, and it tells us the probability, the likelihood of what we saw, given that the null is true. The null being that there is no correlation. So if there is no correlation, this is a likely thing to see. If there is no correlation, this is an unlikely thing to see. Does that make sense? This is a bigger concept, hence why we do a lot of review right here. But this tells us if there is no correlation, this was super likely to see. Like, yeah, that seems very likely. This over here, if there is no correlation, is very unlikely to see. The p-value being the probability. Like, I really don't think we should be seeing this if there is no correlation. So I'm going to say that there is correlation. So it tells us the correlation is due to random chance. No, it says it's unlikely due to random chance. A strong relationship can have a correlation equal to 0. So let's look at this one right here and think about this. How do we tell how strong a relationship is? Is this a strong relationship right here? Is that a strong relationship? So the p-value for the correlation does not imply it implies it's unlikely due to random chance. Yep. Taylor might have to come back and do it. Good questions, Taylor. Thank you so much. I'm going to try to do a little 474 after this. Ooh. If the points are really tight around the form, this has a parabolic form, but the correlation is what? Dots are really tight around a form, right? So this is very strong. This is super strong. So this has an association. So I think a question earlier was, if the correlation coefficient of two variables is close to 0, this implies there's no relationship. So is the correlation here 0? Is there a relationship? So the linear correlation is weak, but there might be some sort of non-linear association. So this is an association. So Evan, to your question, so figure out how yours, will they always give us the value R? They probably will, or for anything it applies for. This would have, it's a parabolic relationship, but if you fit a line through this, the line would not go through it well. Correlation only measures linear relationships. So when you take a look at the question right here, a strong relationship can have a correlation equal to 0. It would just be that the relationship is not what? Correlation only measures this. So if the relationship is not this, there could be a strong relationship. It would just not be this, which we just showed. It would just be that the relationship's not this because correlation only measures this sort of strength. It would not be linear. Great job right there, Wes. So a strong relationship can have a correlation equal to 0. Very true. It would just be a non-linear relationship. And we see that right here where there is a strong relationship with a correlation of 0. That's the top value right there of R. That's correlation. And so the correlation is equal to 0. Correct, I believe, Evan, right? Because yours says, let me look at it again. If the correlation coefficient of two variables is close to 0, this implies there's no relationship. Same thing for this, because look, the correlation is 0. This doesn't imply there's not a relationship. It only implies that there's no linear relationship. It only implies no linear relationship. So great work. We should get that 100 right here. We have just some time. I'm going to try to speed run it the next. But good questions. We can do more versions of this. 10 out of 10. Good lecture review right here. That was mostly the whole chapter. Like, that was pretty much all the concepts. So if you did the Canvas content and you listened through my lecturing of it, you hopefully did a lot of learning right there. Hey, let's go, Brian, right here. You got it. Thank you so much. Love it. Sort of 1,000 points. Always those 10 out of 10s. Did you get a 10 out of 10? Did you get a 10 out of 10 too? Nice job right there. Blake, you get a 10 out of 10. Work for those 10 out of 10s and do your second attempt. Fox right there. Fox is in the chat. Let's do a little 474 to end. I think, Taylor, we might have done that engineer question on another office hours. Traffic engineer recorded the speed of... Yes, we've done that one on another office hours. Tell me if you can't find it. Yeah, you won't be counted off. You don't get counted off for taking it twice. And it's just a good way to practice your knowledge and make sure you understand the concepts, especially if you do it without the video help. You can see where you are, because Canvas content's what the test looks like. Now, remember, you might be like, well, I was acing all the Canvas contents, but you have to make sure if you're doing them, you know, like, are you seeing how you do without my help? So look at the questions first. Let me send out the announcement about class. Woo! Google Calendar. Yes, we have class in 20 minutes. Wait, so Stud, I have 300 more points to get the... Yeah, it's a lot, right? Maybe I shouldn't have spaced it out so much. Maybe I'll do some... It is a lot of points. Do remember, and Blake, great job right there. I don't even know how we got that many. Just here during office hours. Roshni, great job too. We throw out crazy points all the time. I'm trying to make sure I invited to another class. Sure. Oh, there it is. My Canvas is filling up so much. I've got so many courses. All right, let me send out the announcement about class. Good stuff. Maybe one more song right here as we get going. We don't send the announcement, people don't show up. Ah! Class in 15 minutes. See you soon. Click here. Thank you so much, everybody, being here, practicing. Maybe you're watching this later, doing the Canvas content, learning the material. Practice makes better. Okay, we got it. Save, send. Let's go check out. Thank you, John. What is Blake's secret? Just being awesome. TA privilege right there. Just being awesome, just working away, doing some practice. Let me go get that 474 assignment so we can I did some of that. Good. Woo! Ready to get work done. Will you send out an announcement about Sunday's review? You bet, Roshni. Definitely. I'll be sending that out and say we might even do some additional review on Sunday. Just depends. I'm trying to make sure I don't do too much. Sometimes I do too much. And then my body says, "What are you doing, Brian? You're working a lot." Always make sure to get good sleep, good food. Listen to the cars outside making noises. Do that. Listen to cars outside. That's always a good thing. Let me go grab the clustering and number 9. Little clustering to finish up. Pod has fresh sushi. Oh my gosh, fresh sushi would be amazing. I want to get some hibachi. Or some Thai food. Or some, there's a Korean place around here. We got bibimbap. Awesome, some good food right there. Are you going to ship it to Texas or what? Sure, ship it to Texas. Pod Yushi Sushi is yuck. Oh no! Okay, we got just a little bit of time for 300,000 points. We got just a little bit of time right here to do some 474. So we're just gonna do a quick kind of speed run of it of sorts. And let's take a look. Make the screen look a little bit nicer right here. We only got like 6 minutes. Set a 6-minute timer.
6 minutes, starting now.
Question number 8. Looking at the centers of the 3 cluster schemes, the only obvious cluster defining is it number 8 or number 9? Let me double check. Want to do the one 8? Okay, 8. The only defining characteristic is what people are buying in the baby category. Kroger sushi. Though it's clear clusters 1 and 2 are distinct groups since the signs of almost all the clusters are opposite. Look at the centers for the 4 cluster schemes to identify which clusters 1, 2, 3 has been split into 2. Okay. So what we need, and I'm going to run a clustering scheme on the Iris data set. I think, which cluster did we do? Hierarchical here, or did we do we did hierarchical. Good. Hierarchical. So once again, Brian does slightly different work than you. Let's go right here and say example work. We need to run hierarchical clustering on a data set. Make sure your data is scaled. Make sure it's transformed. All that good stuff right there. And we're going to run the H cluster on the Iris data frame. The Iris data frame, we're going to run it on columns 1 through 3. And method, Euclidean? I don't use Euclidean. Let's go right here and use method equals complete. I think it's lowercase. There we go right there. And let's store it into scheme. And there it is, the scheme right there. And we've run it. We should get the cluster IDs out of this. Or I like to say output. I usually like to call this output. So you have done this earlier if you're working on this problem. There we go. Labels. No, where's my labels at? Height, merge, call methods. We want the merge. Oh, I need to cut the tree. Here is my tree. Brian's going too quick. Here's my tree on how things merge. Probably we'd want a 2 clustering scheme. Good to see you here, John. We'd want a 2 clustering scheme for this dendrogram. The best way to look at your dendrograms is where you have separation. To see, we would want either 2 or 3, maybe 4. So if we were going to cut the tree, we would say cut tree, no extra T. Cut tree on our output. And we need to put here that we want there to be, let's say, 3 groups. That means we're probably cutting at a height of something like 3.5. So we could also cut at that height. But here's our cut on the tree right here. And let's store this as output. You can actually see which clusters are merging and splitting if we go to 4. So this cluster right here on the dendrogram would split. So cluster 1, which has a lesser portion of the data, is going to split when we go to the 4 cluster scheme. That's the way to view this visually. So let's call IDs right here. And we're going to store these into IDs, let's say IDs 3. And then we're going to cut the tree and go to IDs 4. So looking at this right here, we're going to go to our Iris data set and store to it IDs 3. And IDs 3 is going to be our grouping for IDs 3. And we're going to do the same thing and store some IDs 4 onto this right here. And let's check out first the data and look at what we've created by adding those IDs. By adding those IDs here, look at those decimals. Let me fix that because I've got my options digits being a little bit crazy. That's Brian's fault, and that should maybe fix the way that looks over there. Woo, much better. So with these IDs right here, these are the 3 cluster schemes right here. You can actually see that we have cluster 2, cluster 3 right there. And then going down further, we should get the 4. Oh, did I not store the 4s? Did I store 3 by accident into it? No, that's 4 clusters. Okay, where's my 4th cluster? Oh, I think the way I cut it. Oh, look at that. There it is right there. So let's redo it, and let's actually store the 4 clusters. And you can see right here, cluster, yep, hey, great job, Morgan, right there. You can see right here, cluster 2 became cluster 4. And we have right here cluster 3. So cluster 2 got split apart. Does that make sense how I'm able to identify this? It was cluster 2. Part of cluster 2 became cluster 4. So there were things that when we did the 3 scheme right here went to cluster 4, and we still have 3 as the same. 3 is still the same, and there's still things that are in cluster 2 that are in cluster 2 for the 4 cluster scheme, and cluster 1 stayed the same. So does it make sense which cluster got split apart? When you look at the dendrogram over here, which cluster it is, the numbers are kind of arbitrary, but which cluster this was right here, this data right in here was cluster what? So we're asking this data right in here was originally called cluster number what? Well, there's the answer. It was originally called cluster 2, and then some of it looks like that smaller portion went to cluster 4, and then this remained cluster 2. So that got split apart into cluster 4 right over here. Looks to be the smaller segment. And then you can see the data as we get down to here. There's more in the cluster 2, which is over there on the right side. And then cluster 1 is the biggest one. That has the most data. You can see all the data points over here in cluster 1, which we're currently scrolling through. And then cluster 3 is a little bit smaller. And that was over here at the start of the data. Oops, didn't mean to make that go away. Cluster 3 is, if you notice, it doesn't have nearly as much data as the other ones. And so we could look at this also and look at the size of this by looking at the counts of the observations. We should see that 1 is probably the biggest. 2, the new 2, which is going to be right there, is the second biggest. 3 and 4. So it should go 1, 2, 3, 4. Really? Maybe it did by size. So if we go here to table of IDs 4, 1, 2, 3, 4, like we said right there. Oh, 2. Whoa. Well, there's my timer. Stop timer. And as it splits, we learn more. It just divides it down into further subgroups. So it's a little bit off. It's 1 and 2 are similar size. 4 is the smallest. It divides it into further subgroups. So we're just segmenting the data more. We might learn more. It just depends. If 3 is good, we look at 4. 4 is good, we look at 5. There is no right answer to this. We're just putting them into more groups to possibly say there's differences among individuals, because that's the whole point of doing clustering. Does that make sense here theoretically, Morgan? So we did a kind of similar example. I didn't scale. I didn't fix my data. I was just running the clustering scheme with complete. You could do a single and get different answers, or Ward's distance, or average, or Euclidean. Lots of ways to do it right here. You're welcome. Great question right there. With that, office hours over. Bye, everyone. Bye.